Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. We are discussing about solid mechanics and material subject. So in this subject, in previous sessions, we have learned what is solid mechanics subject introduction and what are the materials important in solid mechanics and why should we learn these solid mechanics and materials. And after the completion of this course, the student can able to answer whatever we have framed the outcomes. In this part, in this subject, in previous session, we have studied about stresses, types of stresses, strains, and then elastic constant relationships we have seen in the previous sessions. Now in this session, the today's topic is thermal stresses. The topic is thermal stresses. So in previous session we have learned about stresses in composite bars. So what are thermal stresses? What is this? So how to calculate these stresses? We will see in this session. So before going to enter that thermal stresses topic, first we will see the course outcome. It comes under module 1, CO1. The outcome is explain the concepts of stress strain and then material constitutional relationships and strain energy induced in linear and elastic homogeneous and isotropic materials subjected to forces. This is the outcome of this module. At the end of the course, student should be able to answer these points. So the stresses due to change in temperature. So those stresses are called thermal stresses. So whenever there is some increase or decrease in the temperature of a body, it causes the body to expand or contract. So sometimes it may be expand due to changes in the temperature, and also it may be contract due to temperature change, decrease or increase the temperature of a body. So these stresses, mainly this phenomena expanding or contract due to the temperature change in the body. So whenever prevent this expansion or contraction of the body due to this temperature change, then thermal stresses will be occurred. Some stresses will be developed inside the body. Those stresses are called as thermal stresses. So whenever the body is allowed to expand or contract freely with the rise of or fall of the temperature, no stresses are induced in the body. There is no stresses. You are allowing freely the expand or contract. But if the deformation of the body is prevented, some stresses are induced in the body. Such stresses are known as thermal stresses. Clear? So how to calculate the thermal stresses? We will see. So in this, first let's take original length of the body, rise or fall of temperature, that is T, small t. Alpha is coefficient of thermal expansion. So this is the increase or decrease in length. Then increase or decrease in length, that is change in length is equal to delta L is equal to L into alpha multiplied with T. So whenever, suppose a bar subjected to temperature, heat, so it will expand freely. You keep on increasing the temperature, so there is no stresses. Whenever you prevent this increase, contract or increasing, then the inside body thermal stresses will be developed. Clear? So how do we calculate? With the help of coefficient of thermal expansion. So the thermal expansion depends upon the material conductivity, thermal conductivity. It comes under thermal properties. So now you can calculate delta L is equal to change in length is equal to L into alpha T. So it means delta L by L is equal to alpha into T. So what is this? Change in length upon length, original length, is nothing but strain. Strain is equal to alpha into T. As per Hooke's law, stress directly proportional to strain, and stress is equal to E into strain. Strain is equal to sigma by E. See, if the hands of the body are fixed to rigid supports, so that its expansion is prevented, then the compressive strain induced in the body. So the strain name is compressive strain, delta L by L. L into alpha T by L. So we will get alpha T. So thermal stress is equal to, apply Hooke's law, sigma is equal to E compressive strain. So here strain is equal to alpha T. So alpha into T into E. You can write like this. So whenever thermal stresses are present inside the body, you can calculate compressive strain induced in the body with the help of thermal expansion, and stress, thermal stress, that is equal to alpha into T to epsilon. E. Next, linear strain. When a body is subjected to an axial tensile load, there is an increase in the length of the body. Starting already we have in introduction part we have discussed about these strains and stresses. But linear and lateral strain we will discuss now. So when a body is subjected to an axial tensile load, there is an increase in the length of the body, but at the same time there is decrease in other dimensions of the body at right angles to the action of the applied load. So whenever the body is subjected to tensile load, axial tensile load. So suppose example, take one bar, so, axial tensile load is subjected. At the same time, there is decrease in other dimensions of the body at right angles to the action of the applied load. So it means the body is having axial deformation and also deformation at right angles to the line of action of the applied load. The line of action of the applied load is this one. So that is whenever the axial deformation is right angles to the perpendicular to this one. So then that is called as lateral deformation. Perpendicular. So linear. So length. This is length, original length, and deformation length delta L. Similarly, D and delta D. So the length of the body will be increased. This type of strain is called as linear strain. So the ratio of axial deformation to the original length of the body known as longitudinal or linear strain. It means the deformation along the applied load. So longitudinal linear strain. See the linear strain shown in this slide. See, this is a body. The length of the body is shown here L, the original body. Tensile force subjected to tensile force. The force acting on the body. Increase in the length of the body in the direction of P. So this is the action of load along with the applied load. Then change in length. Here linearly the length will be increased. The increase in the length of the body in the direction of P. Then longitudinal strain, the delta L is equal to, epsilon L, that is the strain, is equal to delta L by L. So what is the change in the body and then original length? See, in diameter wise and breadth, the original width is B. The change in width is original length, original width minus change in width. The diameter will be increased. So original diameter and delta D. Length increased and diameter decreased. In this case, linear strain. Clear? So linear strain is equal to change in length by original length. Next, lateral strain. You can represent with epsilon T. So the strain at right angles to the direction of applied load is known as lateral strain. The strain, so applied load is in suppose x direction, the strain will act in this direction, y. So this type of strain is called as lateral strain. So let a rectangular bar of length L and breadth B and depth D is subjected to an axial tensile load P. So the length of the bar will increase while the breadth and depth will decrease. The length of the bar will increase while the breadth and depth will decrease. So let's take delta L increase in length, delta B is decrease in breadth, and delta D is decrease in depth. Increase in length, decrease in breadth, and decrease in depth. So now calculate the lateral strain. Lateral strain epsilon T is equal to delta B by B, delta B by B or delta D by D. So original length, original B minus change in delta B or diameter, change in diameter by original diameter. So these two strains are very important while calculating the Poisson's ratio. So you have lateral strain and linear strain. Now you can calculate Poisson ratio. So already we have discussed in earlier. 1 by m, you can represent 1 by m or mu is equal to lateral strain by linear strain. The ratio will give the Poisson's ratio. So lateral strain delta D by D upon linear strain delta L by L. Clear? So delta D by delta L is equal to L by D. So this is Poisson's ratio calculation. Next, proof stress. What is this? We have seen tensile stress, compressive stress, and shear stress, and normal stress. So what is this proof stress? Some materials like high strength deformed. So that is HSD, high strength deformed steel, brass, and duraluminum, so on, etc. do not show any well-defined yield point. So for these materials, the proof stress serves as analogous to yield stress. In this case, particularly these materials not show any well-defined yield point. Suppose in the mild steel or any other material, take copper, so it shown some yield stress. So already we have learned in stress strain diagram, stress and strain, elastic limit or proportional limit, and then upper yield point, lower yield point, and ultimate stress, and then fracture. So these points B and C and D and E. As you know, so this is upper yield point, lower yield point. But in this case, some materials like HSD steel, brass, and duraluminum, so it does not show any like this well defined. This is upper yield point and lower yield point. So before deformation, before deformation, it shows some yielding. Upper yield. This is lower yield. Ultimate stress. Ultimate and fracture point. Okay. So proof stress is the stress that is just sufficient to produce under load a defined amount of permanent residual strain. So which a material can without appreciable structural damage. This arbitrary value will be different for different materials or different uses of same materials. It's just sufficient to produce under load. So material have without appreciable structural damage. So arbitrary value will be different for different materials. This proof stress value. So that is depends upon the structure of the material, and then the application of the material, the different uses of same material. See in this shown the proof stress diagram, the proof stress and proof resilience. So here see stress versus strain drawn diagram, and up to this point. So 0 to a elastic limit and torsional limit. So at this point, the proof stress shown here in triangle. So the yield stress occur at this point, upper yield point, and then the proof stress or that is proportional stress, the proportional stress up to elastic limit shown in this diagram. Clear? So what is the percentage here? Yield stress 0.01, and then here see from strain 0.2% strain. So in this, so the amount of permanent residual strain produced under load, the strain will be occurred inside that residual. That is called as proof resilience. Whatever strain energy stored inside the body at yield stress. Proof stress and particular stress is called as proof stress at a particular point, that is at a yield point. Clear? So it is nothing but sufficient to produce under load. So whatever stress shown in this diagram, yield stress and professional stress. So next one, you'll see one problem, numerical problem related to this thermal stresses. So in this, what he has asked, so a thin steel tire is sunk on to a locomotive wheel of 1.2 meter diameter. So find the internal diameter of the tire if after shrinking on, that is hoof stress in the tire is 100 megapascal. So assume here the this Young's modulus or modulus of velocity is 200 kilonewton per mm square. So what he has asked, find and also find, first to find internal diameter, that is d, small d, and find also least temperature to which the tire must be heated above that of the wheel before it could be slipped on. So what is the temperature required? Must be heated. The coefficient of linear expansion for this train is 6.5 into 10 to the power minus 6 per degree centigrade. So thermal expansion, linear expansion, that is alpha given. So this type of problem by using thermal stresses relations. So already you know thermal stress relation, delta L by L is equal to delta L is equal to delta L by L is equal to alpha T, or delta L is equal to L into alpha T. And stress is equal to thermal stress is equal to E into thermal strain. So now we'll see first given data. For any problem, first you should write the given data. Given D is equal to the outer diameter 1.2 meter, that is 1200 mm. The sigma, that is Joule stress 100 megapascal, convert into Newton per mm square. You know 1 megapascal is equal to 10 to the power of 6 Pascal. So 1 Pascal is equal to 1 Newton per meter square. So that 10 to the power of 6 Newton per meter square. Convert into mm square, 10 to the power of 6 by 10 to the power of 6 Newton per mm square. So you will get 1 Newton per mm square. 1 megapascal is equal to 1 Newton per mm square. So that the 100 megapascal converted into Newton per mm square. So almost 100 Newton per mm square. So similarly, the Young's modulus E 200. So 200 kilonewton per mm square. So 200 multiply with 10 cube. 200 multiply with 10 cube Newton per mm square. So alpha is equal to 6.5 into 10 to the power minus 6 for degree centigrade thermal expansion. So now we will see how to calculate the thermal inside diameter and outside diameter. So first, let small d is inside diameter. So here, the steel tire is shrunk onto locomotive wheel of bigger diameter given, capital D given, and after sinking the boot stress also given, that is 100 megapascal. So now here the stress is equal to, stress is equal to load per area. But if our load not available and area also, where we can calculate. But one more relation is there. According to Hooke's law, stress is equal to E multiply with strain. Which type of strain here? Lateral strain. So E multiply with lateral strain, that is epsilon L. So what is this lateral strain? Is delta D. So that is delta D by D. So diameter will be increased. So the dimensions are changed perpendicular to the load applied. So delta D is here change in diameter, and then small d is the original diameter, inside diameter. So now you can write this equation. So here you can write stress. So this is nothing but here wove stress. The wove stress in the tire is 100 megapascal given. This is equal to Young's modulus or modulus of elasticity E multiply with strain delta D by D. So now you can write E capital D minus small d by small d, original length. So here wove stress. Now substitute the given values. So otherwise simplify this equation first. Capital D by D minus small d is equal to sigma by E. Right? We can write like this. So further simplification, capital D by small d minus 1 is equal to sigma by E, you can write. So again, you can write capital D by small d is equal to sigma by E plus 1. Clear? So now substitute the given values in this equation. So what is the final one? Capital D by small d is equal to sigma by E plus 1. So here substitute the given value. Capital D is 1200 mm, 1200 by small d we don't know, and sigma also you know 100 Newton per mm square, and E 200 into 10 cube Newton per mm square. 100 Newton per mm square by 2 into 10 cube. Sorry, 200 into 10 cube. Plus 1. So simplify this equation. Small d you will get inside diameter. So 1200 by here 100 by 2 into 10 to the power 5 plus 1. So get cancelled here 2 zeros, and 1 by 2 into 10 cube plus 1 200 by d. So simplify this equation. The capital D, small d, you will get so here small capital D is so much given, capital D 1200 mm. The small d you will get the inside diameter 1198 0.0 mm approximately will get. So inside diameter. So now next one, what he has asked, find also the least temperature to which the tire must be heated. So here, so temperature, so next one, next calculate temperature. So in this, in first step, we have calculated internal diameter, and then also least temperature to which the tire must be heated. The above heat of the wheel before it could be slipped on. Here, so let take let T is the temperature. So the given area, the given wheel perimeter 2 pi r, So apply those formula for here, that is pi d is equal to the outer perimeter is equal to inner pi d plus phi d into 1 plus alpha. So here you will get alpha t. So expand this one, pi d is equal to pi d plus phi into d plus pi d alpha t. So here 2 pi d plus pi d alpha t. And a capital pi d. So take alpha t. So take alpha t here, take outside, you will get capital D minus small d by original diameter d. Take phi common here, d minus d. So we will get the final equation is alpha t is equal to d minus d by small d. But here you need to calculate temperature. So the temperature is here. So write this equation like this: alpha t is equal to capital D minus small d by d. This is after simplification, you will get this relation. Here, take outside temperature d minus d by t divided by alpha. So this is temperature, least temperature to which the tire must be heated. So that substitute in equation. So least temperature is equal to capital D. The capital D is how much? The capital D is 1200 mm. So 1200 mm minus 1198 minus small d divided by alpha. So alpha value is 6.5 into 10 to the minus 6. 6.5 multiply with 10 to the minus 6. So once again write this equation. 1200 minus 1198 by 1198 upon 6.5 into 10 to the power minus 6 degrees centigrade. So here approximately 2 by here 1198 mm divided by 6.5 into 10 to the power minus 6. So calculate this equation. So simplify. So after determining, you will get approximately this value 71 degrees centigrade. So the least temperature required, the heat, the temperature must be heated above that of the wheel. So before it could be slipped on. So the thin steel tire is shrunk onto a locomotive wheel. So the wheel diameter given, the tire, the inside diameter of the tire also we have calculated. That is shrunk onto a locomotive wheel. For this shrunk fitting, so what is the temperature required? So that is we have calculated, so that the 71 degrees centigrade is required to which the tire must be heated, so above that of the wheel before it could be slipped on. So this depends upon the material thermal expansion coefficient. So like this you need to calculate the thermal stresses. So suppose here in this problem he has given that the thermal stress, the sigma, that is a Wolf stress. If not given, remaining values also available. Then how do you calculate this thermal stress? Thermal stress is equal to E into thermal strain. So what is this thermal strain? E multiply with delta L by L. This is linear strain. Linear strain. So you can calculate thermal stress is equal to E into delta L by L. So already this condition we have seen in this thermal stress equation. See, in this thermal stress is equal to sigma C. This sigma C given here compressive strain. Sigma C into E is equal to alpha T into E. So if you know the temperature, you can calculate the alpha already given. That temperature, if you know, you can calculate thermal stress. Clear? So sometimes they will ask like that also in examinations. The compressive strain is equal to alpha T. Remember this equation. So in this problem, we have seen the temperature required, the least temperature, and also calculated the internal diameter. So now in this session, so we have learned thermal stresses. So in this thermal stresses introduction, we have learned. So what do you mean by thermal stresses? And then so how do you calculate the change in temperature, change in due to the temperature change? What is the change in length and change in diameter? So that is depends upon the coefficient of thermal expansion, increase or decrease in length. You can calculate. So similarly, you have studied thermal stress equation formula and then linear strain. So the definition of the linear strain and then lateral strain. So how to write these two equations we have seen, delta L and epsilon L and epsilon D. So lateral strain we have seen in this through example rectangular bar of length L. The lateral strain delta B by B or delta D by D. So and also we have studied this Poisson's ratio. The Poisson ratio is nothing but it is the ratio of lateral strains to linear strain. So that's why first you should know the lateral strain and then linear strain and then apply the ratio. It gives Poisson's ratio. So this is the Poisson ratio depends upon the material properties. So in examination, while problem solving, they will give the Poisson's ratio. If not given, you have to assume the Poisson ratio for particular material. Or if you know the lateral strain or linear strain, you can calculate. So by using this lateral strain formula and linear strain formula. So that is depends upon the material and then the application, the Poisson's ratio. So this ratio is important in elastic constants relationship. The relations already we have seen in previous sessions. And also proof stress. So in this, you have seen what do you mean by this proof stress through diagrams. You have learned. So what is the difference between this normal stress and then elastic limit, proportional limit stress and this proof stress. And finally, you have seen thermal stresses problem, how to calculate the thermal stresses. Clear? So in this, we have calculated thermal strain and then thermal stress. So by using the thermal stress relation, so apply here Hooke's law. So this is Hooke's law. Already we have discussed about this Hooke's law in earlier sessions. The stress is, this law states that the stress is directly proportional to strain. So whenever the stress increased, the strain also increased equal amount. Stress decreased, strain also decrease. So that's why it's directly proportional to the strain value. So this is depends upon the material property and then depends upon the load up to within the elastic limit only. So beyond this elastic limit, it not follows this Hooke's law. The stress suppose increase, the strain increase in different way, not exactly equal to the amount of stress value. It reaches the ultimate yield. It reaches the yield stress, upper yield stress and lower yield stress, and then reach to the maximum ultimate stress. That is maximum stress. Beyond this ultimate stress, it fails. That is fracture point, breaking point. So we have seen in a stress strain curve. So that this ultimate stress or maximum stress we have used in the calculating the factor of safety topic. The factor of safety already we have seen the factor of safety topic learned in earlier sessions. We will take this maximum ultimate stress in while calculating the factor of safety. Factor of safety is nothing but maximum ultimate stress to the working stress or design stress. So how much it can withstand, that is the maximum value, and how much load you applied. Clear? So based on this, the factor of safety will calculate to be calculated. For every design engineer, before designing, the design engineer should take the factor of safety. So then only the component will be in safe condition without fail. The factor of safety is nothing but to avoid the failure for safe design. Clear? So up to within elastic limit only the Hooke's law follows, and beyond this point it does not follow the Hooke's law. So the thermal stresses also, the change in temperature. So whenever whenever you have prevent this expansion or contraction, the thermal stresses, the inside the stresses will be developed. Those stresses, thermal stresses, and how to calculate we have seen in through this problem. And also here temperature in this problem, how to calculate temperature if you don't know the temperature. So least temperature required to heat the in this problem given the shrunk feet. So first need to calculate, need to apply the Hooke's law, and then apply thermal stresses formula. So delta here the strain, the lateral strain is equal to alpha T. So lateral strain, delta epsilon L, delta D minus D by D, small d by small d. So change in diameter upon original diameter. Divided by alpha, that is the coefficient of expansion. The temperature, thermal stresses always depends upon this coefficient of expansion only. So thermal expansion is different for different materials. So nothing but thermal expansion influences the thermal conductivity. So thermal conductivity, it means that it comes under thermal properties. So I have calculated by using this relation. So that is alpha is equal to you will get, temperature will get 71 degrees centigrade. So like this you have to calculate the thermal stresses. So up to now we have seen these topics. So for this PPT I have taken references Ramamurtho, strength of materials, Dhanpati Rai and R.K. Rajput, the strength of material title and Chand publication, and R.K. Bansal, strength of materials, Lakshmi publications, and R.S. Kurmi. So these are the references I have taken for this PPT. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.